Hi everyone. In this video, as part of the manual, I'm going to be discussing nuclear radiation. This involves unstable isotopes, so that's to say nuclei of elements that have different numbers of neutrons decaying into more stable nuclei through the emission of some form of nuclear radiation. So there's three types of ionizing radiation you need to know about at GCSE, are alpha, beta and gamma radiation, and I'll discuss the differences between them, both in terms of their ionizing properties, so their abilities to kick electrons out of atoms as they move through materials, and in terms of the particles they're made of throughout this video. This is something you've already studied, and now's a great time to pause and jot down everything you can remember about this topic. And otherwise, I'll get started on the whiteboard. So the modern day model of the structure of the atom was actually born from a famous experiment by Ernest Rutherford over 100 years ago now. So this experiment told us that actually atoms are made of small positively charged nuclei with electrons orbiting around the outside. To begin with, people thought that nuclei were just made of one type of particle, the proton, but we now understand that nuclei are actually made of protons and neutrons. If you can consider the chemical symbol for a given element, I'll call it X, A, Z, where X is the chemical symbol. I'll give it a few seconds, my whiteboard's being slow today. A is the mass number. And Z is the atomic number. So A, which is the mass number, is actually the number of protons plus the number of neutrons in the nucleus. Whereas Z is the number of protons in the nucleus, which is equal to the number of electrons when you have a neutral atom. And of course, that means the number of neutrons in general is going to be A minus Z. So if you look in the periodic table of elements, which classifies the different chemical elements in order of increasing proton number, you'll see that some elements actually have a mass number that's not an integer, so it's some fractional number. And therefore the reason for that is actually many elements have several common isotopes. So an isotope of an element has the same Z, but a different A. So i.e. a different number of neutrons in the nucleus. So a common example is the element carbon actually has two common isotopes, carbon-12 and carbon-14. And actually carbon-14 is often discussed when considering radioactive carbon dating. So carbon-14 nuclei are unstable, so will decay. The numbers you see in the periodic table are actually a weighted sum of the mass numbers of the different isotopes of a given element that are weighted by their relative abundance in nature. So for most elements, they only have 1 or 2 stable isotopes, and other isotopes are unstable, meaning their nuclei will decay through emitting some radiation into a more stable nucleus. And a typical process for this will involve, let's have some A1, Z1, and I'll call this is my unstable. That will decay to Y, which will have, A2, Z2, plus some type of radiation, which I'll discuss soon. And in some cases, it also the process might also lead to the release of some neutrons to rebalance the number of protons and neutrons inside the nucleus. So when I say rebalance, the number of protons and neutrons inside the nucleus doesn't have to be equal for a stable nucleus. For low values of the mass number, this might be observed to be the case, but what I mean is rebalance it to a value of A that corresponds to a stable nucleus. Okay, I'm now going to discuss the different types of radiation and also the symbols that you might have to use to write these into a nuclear equation. So when you're writing a nuclear equation like the one I've written on this whiteboard, both the mass number and the number of protons, so the Z number, has to balance. So as I said before in the introduction, the radiation given off in nuclear decay is what we call ionizing. So it has the ability to kick electrons off atoms as it travels through a material. And how ionizing a type of radiation is can impact what you might want to use it for, but also its potential risks from exposure, because obviously very ionizing radiation could cause damage to materials it travels through, including human tissues. Okay, so there are 3 types of radiation we need to discuss at GCSE level. There's alpha radiation, there's beta radiation, and there's gamma radiation. So alpha particles are actually helium nuclei. So the nucleus of helium-4. So that means that they're made of 2 protons plus 2 neutrons. That means they have a plus 2 in units of the elementary electric charge. And actually, compared to the other types of radiation, they're relatively heavy and typically won't travel very far into a material before being stopped. So they typically can be absorbed either by a very short distance in air or by a sheet of paper. However, because they're relatively large, alpha particles are strongly ionizing. So they have the highest ionizing power of the 3 that we're discussing today. So beta particles are high-speed electrons. So I'll write the symbol here. E 0 because I have no protons and neutrons in, but I'm going to write the mass number as, the proton number here as -1. And the reason for that is that when you have a beta particle emitted, so a high-speed electron emitted, you have a neutron converting to a proton inside the nucleus of the atom. And following the trend from the previous alpha particle that we discussed, beta particles are what we would say are moderately ionizing. So actually, they lie between alpha particles and gamma radiation on the right-hand side. So actually, they can have a range of around a few meters in air, but could also be absorbed by a sheet of aluminium. Okay, so then let's go on to the final example, which is gamma radiation. So actually, this is short wavelength electromagnetic radiation. So it's a wave. For the level we're working at GCSE, you can think of as alpha and beta radiation as, I guess, both being particles, and gamma radiation being an EM wave. This is, I guess, a kind of cool hint for something you will go on and study maybe in a bit more detail later on, where we might start to think about light as also being made of packets when you study something called quantum physics. Okay, so continuing with gamma radiation, so it's weakly ionizing. So it can travel very far into materials, and actually you'd need a big block of either lead or concrete in order to stop gamma radiation. Okay, so I think I've said what I want to say about alpha, beta, and gamma radiation now, but I guess maybe just to bring it all together a bit, as I go across from alpha to gamma, we get more penetrating, but less ionizing. And you should practice being able to write nuclear equations involving alpha, beta, and gamma radiation too. So for alpha radiation, if you emit an alpha particle, the mass number of the nucleus must decrease by 4. So the atomic mass, that's to say, and the proton number must decrease by 2. And it might be in your equation that extra neutrons may or may not be emitted to balance, but hopefully in the most simple case, so A1 would be A2 plus 4, and Z2 would be Z1 minus 2. For beta radiation, an easy way to spot it is the atomic mass number, so the A value won't change, but the Z number will reduce by 1 because one of your neutrons is converting to a proton. So for gamma radiation, because this is an electromagnetic wave being given out, there's actually no change in the number of protons and neutrons inside the nucleus here. So gamma radiation typically occurs when what we call an excited nucleus, so a nuclei in a higher energy state, gives off radiation to move into a lower energy state. So one interesting thing about nuclear decay is that it's a random process, so you can't say for sure when any given nuclei is going to decay, but you can describe the properties of a radioactive substance on average. So when you have a large collection of radioactive nuclei. And there are two properties that you often meet when describing radioactivity. So the first is the activity of a radioactive substance. Activity. And that's the number of decays per second that are occurring in a given radioactive substance. And this has a unit of what we call becquerels, BQ. So the second term that we often use when discussing radioactivity is the idea of half-life. So assuming that actually our radioactive process involves an unstable isotope turning into a stable nucleus, possibly of another element. So the half-life corresponds to the time for the number of radioactive nuclei in a given isotope to half. And actually, the reason that half-life is a useful quantity is that actually, if you think about it, if the half-life of a substance is constant, so after any given time, the number of radioactive nuclei left halves, you can hopefully see that the activity, so the number of decays per second, is never actually going to get to zero. It's just going to be getting smaller and smaller and smaller over time. And you can view the half-life on a graph of the activity over time, or the number of radioactive nuclei over time. So activity follows an exponential decay here, and if this is our starting value, I'll try and mark out half here. So this time here will be the time when the activity halves, or the number of radioactive nuclei halves, is then the half-life T half. And I'll call this activity versus time. Well, there we go. Okay, I hope this has been useful. I hope you've enjoyed either learning about or recapping about the different types of nuclear radiation. Please keep sending in questions or requests for further topics if you have some, and otherwise have a nice day, and I hope to see you all soon.